In this video, we present a vision-based relative detection and tracking for teams of microaerial vehicles. There are two main parts to this paper. First, we designed several multi-tracking filter strategies to resolve the association problem and provide a comparative analysis on the trade-off between accuracy and computation complexity. Second, we demonstrate the pipeline running all on board in real time on a small fleet of swap-constrained robots. We investigate how robust a tracking filter is by observing each drone's trajectory, shown here in different colors, is correctly associated over time. In high occlusion scenarios, or when the drones are crossing trajectories, maintaining correct associations become difficult. In our comparative analysis, we analyze 3 Bayesian filters that are representative of several tracking categories. We evaluate their performance on their robustness to occlusion, as well as various measurement noise. We do this analysis for all 3 filters, the common filter, joint probabilistic association filter, and the probability hypothesis density filter, and observe that the PhD filter is the most robust in high noise scenarios. We also investigate the trade-offs between tracking accuracy and computational complexity for swarm applications. Here we have 8 drones crossing trajectories. Computing the possible association between new measurements with the existing track is the computational bottleneck for the tracking filters. Although JPDF tracks slightly more accurately, we can observe that the computation for the JPDF filter grows exponentially with the number of tracks, so we instead employ the PhD filter here, which scales much more manageably. With the conclusions obtained from the comparative analysis, we demonstrate the PhD filter on real hardware encased with noise and heavy occlusion. Here we can see that the filter is maintaining correct tracks for each agent, shown in green. And although there are some measurements shown in red that are missed for a couple frames, we see that the tracks are maintained.
Lastly, detection and tracking can run on each robot in a decentralized manner as the 3 drones move in a predetermined trajectory. We show the perspective on all 3 drones at the top. We can see that the perception consensus is achieved in that even though tracking is done local on each robot, all drones share the correct ID and state among each other.